guys, and welcome to the cell section of the Just-in-Time series. Now, in this section we'll cover what a cell is, why we even use cells, the different types of cell variations, and how to create cells. But before we get started, here's a little intro into the subject. Have you ever watched little kids play soccer? They all surround the ball and kick aimlessly. In these massive piles of kicking kids, the ball happens to squirt out and the process repeats itself. Sometimes goals are scored, but usually little is accomplished and everyone just leaves tired. Now, running a relay race is a totally different sport, but kids seem to pick this up a lot better. Perhaps it's because they're forced to play the game in fixed lanes. Each child runs his or her leg of the race and passes the baton towards victory. Think for a moment, how does value flow in your organization? Do you always have jams, bottlenecks, and backups that are constantly shifting? Does your organization respond by collapsing around the jam in an unorganized manner, just like these kids playing soccer? Does a ball just squirt out in the form of another jam? Well-designed cells allow for workers to play their position. Good cells, like relay races, don't have log jams. They allow for value to flow smoothly from supplier to customer. In a relay race, it's not necessarily the team that has the fastest runners that win. It's the team with the fastest runners on average. So that team with the fastest runner in the world, running anchor, may actually lose because other members of his team aren't fast enough. This should be encouraging to those of you with shops with aging equipment. You may not have the latest class of super widget makers, but do you really need it? In all likelihood, other pieces of machinery downstream can't keep up anyways. There's also the teamwork aspect of running relays. Remember, there needs to be a successful handoff of the baton between runners. If you drop the baton, you're probably going to lose, regardless of how fast your team is. The same can be said about machinery in a cell. Are the machines in a good sequence to pass value? Or are they improperly sequenced and spaced so far apart that the baton, in the form of work in process, drops between every station? Simplex Ski Company is a traditional manufacturer. As such, the shop floor is arranged as a process village. This means that like machinery is grouped together in large areas. This traditional model is one of many remnants from the era of mass production. The issue with process villages is that it impedes flow and encourages overproduction. This is Simplex Ski Company today. The shop floor has been rearranged and machines have been placed in sequence of production according to value streams or product families. These are known as cells. So here are some characteristics of what a cell is. First of all, they're focused areas where value is added quickly, generally one piece at a time. They're made to be flexible, so if your demand happens to spike, you can change your cell to accommodate. And last, they're designed to minimize non-value added activities. So this is what I mean by focused. Cells are designed to meet the demands of a specific product family or value stream. In this example, the cell to the left only completes skis for the yellow value stream. The cell in the middle is for the blue and green product family, and the red cell runs on the right. Flexibility is also the characteristics of a well-designed cell. Workers are trained to quickly respond to changing customer demand. If demand decreases, then workers respond by systematically leaving the cell. Those that remain know exactly what tasks they need to perform to meet customer demand. Machinery is also flexible. Oftentimes, cells have to be rearranged during setups to accommodate different products. We've placed casters on machines to make them mobile to increase the flexibility of the cells we've created. Finally, cells minimize non-value added time because they're designed to make products flow to completion, generally one at a time. In the process village model, inventory builds up between functions, adding non-value added time. In cells, products flow from start to finish without stopping, so non-value added time is minimized. So there are many ways you can arrange your cell, but these are the 5 most common types. First of all is the all too familiar circuit. Then you can do the split work type. You can use reverse flow. There's the combination of the above. And then finally, the ratchet. So let's go through each type in detail. This is what a circuit looks like. An operator, or in this case more than one operators, work the entire loop and take the product from beginning to end. They complete the entire circuit repeatedly. In a circuit, there's generally not much work in process because the workers carry and complete their product from beginning to end. One disadvantage is that each worker has to know how to complete the product from beginning to end, so there may be more training involved to run a circuit. There are also no successive checks between operators. Each operator completes all tasks from beginning to end, so there's less opportunity to catch errors. Next is a split work cell. We utilize Adam Smith's division of labor and divide all the tasks needed to complete the part between numerous operators. This is what people generally think of when cells are mentioned. Now, some argue that the number of handoffs should be minimized. I've actually found the most success when the number of handoffs are maximized. This is because each handoff serves as a check of the previous operator's work. So there are more successive checks built into the process as handoffs increase. A split work cell usually has a relative short learning curve because each operator only has to learn a small portion of the work needed to complete the part. However, it's important to rotate workers so they gain a wider range of skills and they don't get bored. Next is a reverse flow model. This is basically running the circuit in reverse flow. So here's how it works. There is standard work in process at each station. The worker pulls a complete part from station 3 and places it in the finished goods supermarket. He then takes a part from standard whip and places it at the machine at station 3. He removes a part from the machine at station 2 and places it into standard whip. He takes a part from standard whip between stations 1 and 2 and places it into the machine at station 2. He replaces that with a part that came off of station 1. He then takes a part from raw goods and starts it at machine 1. The process then repeats. By this time, the machine that was processing the part at station 3 is complete, so the loop starts over without interruption. So as you can see, in this reverse flow model, each station had to keep a piece of standard whip. But this whip allowed the worker to continue moving without having to wait for the machine to process work. This is what it looks like in real life. Everyone knows the normal circuit for washing clothes. I'd put the clothes into the washer, then wash, then dry, then put the dry clothes into the clean basket. But it takes about an hour and a half per load. On this day, I have lots of laundry to do. So I decided to run a reverse flow cell. I remove the clean clothes, load the dryer, empty the washer, and load the washer. Now I see a clean load of laundry coming off the line every 45 minutes. This is a combo cell. Notice there are two different techniques used in one cell. You can see the split model work, and you can see the circuit between stations 5 to 7. You can mix and match all these different cell types to suit your needs, so don't feel obligated to use just one. Mix and match to produce products efficiently and to meet customer demand. This last example is called a ratchet. So if you find yourself in a situation with 6 workstations but only 5 workers, this model could work for you. You'll be getting one piece every complete ratchet of the line. So workers ratchet back and forth between 2 stations. Again, each time the line ratchets, a complete part is produced. So when designing a cell, you should have a very good idea of what your total work content is. Lay all those activities out on paper, and then do a quick paper Kaizen. Cross off those activities that are completely non-value add that you don't need in the first place. Then decide, do you want your cell to be a mixed system or a dedicated cell to a single product? I've seen both work, that's your choice. Next, a multi-skilled worker environment works great because if a worker can work on multiple machines, that cell is all the more flexible. Lastly, you're going to need excellent standard work to document how you want your cell to work. So like I just said, you need a good understanding of the total work content. Now, before you start slicing and dicing these tasks, take time to do a quick paper Kaizen activity. You'll be able to save a lot of time if you just take the time to eliminate those tasks that are non-value added and aren't necessary in any way. You might be surprised as to how many tasks you're able to eliminate. Your tack time, your machinery, and your workforce are going to dictate how you divide your total work content. Keep in mind that cycle times at each station have to be less than tack time. Otherwise, you won't meet customer demand. Each worker should understand the work that needs to be completed and the timing in which he needs to complete each task. When describing cells, Taiichi Ohno used a running relay as opposed to a swimming relay. The reason he did this is because swimming relays have discrete points for handoffs. In other words, a swimmer has to tag the wall before the next swimmer can jump into the water. In running relays, the next runner begins running before the baton is passed. This happens in a legal baton passing zone. Cells are set up much in this way. Each operator has a designated set of tasks that are represented by the white cells. So the highlighted tasks are those that either station can perform. If the operator at workstation 1 observes the operator at station 2 struggling momentarily, he can help out by completing the shared task. These shared tasks serve as buffers and keep the line running at an even pace. Now that you have a good understanding of how to divide work content among your workers, it's time to begin thinking about the amount of inventory you want to keep in the form of standard work in process. When I ask this question, the standard answer that I get from those that are new at Lean is to keep 0 inventory. This is not the case. Remember, while inventory is a form of waste, it can also be an important ally. If you recall from our standard work section, I kept one piece of toast in standard whip so I wouldn't have to stop and wait for the toaster every single time I wanted to make a sandwich. Those pieces of bread in the form of standard whip let me continue working through the cell. So let's explore how inventory in the form of standard WIP helped our paper airplane factory in the simulation series. To make the math easy, let's assume that the cycle time at each station is 1 minute. If I only allow one plane of WIP in the system, then I'll only see a plane come out every 4 minutes. This is what it looks like. Notice workers 2, 3, and 4 don't have anything to do, and so they're idle. Now station 2 has a plane, and workstations 1, 3, and 4 are idle. They pass the plane along, and 4 minutes later, it pops out. I observe at station 4 a plane being completed every 4 minutes. This turns out to a throughput of only 15 planes per hour. Now let's allow 2 pieces of standard WIP in the system at any given time. Stations 1 and 2 have something to do, and stations 3 and 4 are idle. A minute later, they pass the work, and now 2 and 3 have the planes. Now a minute after that, stations 3 and 4 have work, and 1 and 2 are idle. One plane finally completes, so workstation 1 is allowed to have a plane in standard WIP. This model gives me a throughput of 30 planes per hour. Do you see how we just doubled our output by adding another piece of standard WIP? We do the same for 3 pieces in WIP, and we find that the output is 45 planes in an hour. Only when we allow 4 pieces in standard WIP do all workers have something to do at all times. I observe planes being completed 1 per minute in this model. It turns out to 60 planes per hour. We just quadrupled our output from the original model by allowing them to have more standard WIP. So next time someone tells you zero inventory is the goal of lean, walk them through this simple example. Now cells can take many shapes, but perhaps the most popular is the U. Now people like it because the incoming and the outgoing are right next to each other, but there are other shapes that worked really well too. I've seen L-shaped cells work well, and I've also seen linear cells work well too. Now there are 2 shapes to avoid. The first is the bird cage, and last is having the operators located on the outside of your U. Everyone defaults to a U shape when they think of cells. Now I like U shapes, but I try to keep in mind that they may not fit the working environment you're in. The yellow cell you can see is arranged in a straight line. The blue and green production cell was arranged in an L. The shape of the work area made the L favorable. Just keep in mind that you shouldn't feel locked into a particular layout. Carefully consider which shape works best for you and your organization. So there are many shapes that will work, but I'm going to show you a couple shapes that should be avoided. The bird cage looks something like this. There are a couple reasons why this is not a good shape for your cell. First of all, there's a safety risk. In the event of a fire, how are workers supposed to exit the cell? Secondly, the workers completely lose line of sight of each other. In other shapes, they can quickly take a glance over to see the next station to see if they need help in passing the baton. In this model, they can't. Now this is a U-shaped cell, which is fine. But the issue is the operator's on the outside of the cell. I know you won't be able to avoid this all the time because some machines are built to flow in the opposite direction of your cell. But try your best to keep operators on the insides of cells so they can help each other out when they get into a pinch. In this model, operators have to walk all the way around the cell to help each other. I mentioned earlier that you'll have to decide if the cell will be dedicated to one product or if it will be a mixed model system. In this example, we have 2 dedicated cells. The cell on the left is dedicated to red triangles, and the cell on the right is dedicated to blue octagons. One advantage to having dedicated cells is you can have specialized machinery dedicated to that particular product you're producing. You'll also have a shorter training period because workers only need to produce one product. Dedicated cells also allow you to avoid setups, so you may get a higher throughput through this configuration. Your other option is to have a mixed model cell. In both of these cells, red and blue pieces are being produced. An advantage of this is if one worker happens to be absent, you can still get both product types produced. This model is actually more disciplined because it forces you to reduce setup times and think in terms of leveling and cross-training. So long term, this model has an advantage over the dedicated cell model. Again, both types have their merits, so carefully consider how you want to run your cell. I've mentioned several times the benefits of having good capacity linearity. In cells, it's also important. If one operator can produce 5 units, 2 should be able to produce 10, and 3 should be able to produce 15. Actually, as you add workers, the output per worker will increase. But let's assume a linear model for now. So this is a cell with 1 worker. Notice he produces 5 triangles. This is the cell with 2 workers, and they're able to make 10 at the same time. This is the same cell with 3 workers, and they're able to produce 15 in the same amount of time. Now, your model will likely not be perfectly linear. But it's important to have a good understanding of the output based on the number of workers you have in the cell. You can then add and subtract workers in the cell to match changing customer demand. So now that you know how much each worker outputs, you now need to know the theoretical number of workers you need as demand or takt time changes. This is a simple calculation. You take your total work content and divide by the takt time. In this case, your total work content is 75 seconds and our takt time is 30 seconds. This means we need 2.5 workers to meet takt. We rounded up to 3 because we can't have half a worker. So this is what our load chart looks like with 4 workers. And this is what it looks like with 3 workers. Obviously, there's a lot less idle time with 3 workers. When you use this equation, there's a high likelihood that the numbers aren't going to divide evenly. So what do you do with that extra fraction of a person? Here are some rules of thumb. If the fraction is less than 0.3 of a person, then round down. You'll be amazed as to how the remaining workers quickly absorb work and still meet takt time. If the fraction is between 0.3 and 0.5, then round down and try to Kaizen that area for the next 1 or 2 weeks. If they still can't meet takt, then add the person back. As a side note, I've never had to add the person back after this Kaizen period. Now, if you're stuck with a fraction that's 0.5 or greater, then round up. So let's say the equation tells you need 4 people to meet takt. Over time, you'll naturally observe workers getting better and better at their tasks. You have a few options. The first is simply allow more idle time in your system. Idle time is obviously waste. You know that in order to drive up efficiency without overproducing, you're going to have to remove a worker. I've found that the best way to do this is to target the last worker in the sequence. I let the team know that the goal over time is to absorb the tasks of the 4th worker while still meeting customer demand. I also make sure that the worker being removed is the best and most versatile worker in the group. This way, I'm able to move him to another area where he's able to pick up another skill set. I've also found that the best workers generally have the best attitude and are willing to move to other cells to learn. Don't make the mistake of targeting and removing the worst performing worker. This will hurt morale and send the wrong message. Now you need to consider how materials will be replenished in your cell. I like gravity-fed racks for many reasons. First, they're intuitive. The top rack carries full bins and the bottom rack carries empty bins. Notice they don't require any power. Gravity pulls down the next item to be produced and gravity pushes away empty bins towards the material handler. Another reason why I like them is you can sequence what needs to be produced. If the rack were flat, an operator could accidentally pull the wrong item. But gravity forces the next item in the sequence toward the operator. So this is what it looks like from above. The material handler visits each station. He removes empty bins and replaces them with full bins in the exact sequence they are being consumed. After the material handler is done with his round, he goes back to the supply area to refill the empty bins he just picked up. Notice that we keep the supply area far away from the cells. This is by design. Operators going to refill bins is not part of their standard work. If they run out of parts, we don't want them to replenish their own bins. If supplies were located close by, they'd be tempted to do so. If they keep refilling their own bins, this masks issues with the material handling area. Remember, we want to expose opportunities for improvement, not mask them. So in closing, one of the first organizations we worked with took us on an initial tour of their facility. The operations manager was proud and wanted to let me know the team environment the company had. He told us how the shipping department often gets jammed up, so the office personnel, sales rep, and even the VP roll up their sleeves and ship product. This favor was returned about once a week by the shipping department when the front office was in a jam. It wasn't until after we were able to smooth the process did the operations manager realize the flaw in his previous teamwork statement about the organization. So take a moment and think, is your company organized to allow value to flow smoothly from beginning to end like this well-organized relay race? Or do you spend more time aimlessly huddling around soccer balls in the form of log jams and daily fires? So here's a quick summary of what we learned. We defined what cells were, we explored the different types of cells, we looked into creating cells, and we took a deeper dive into standard work in process.